Previously, we talked about discrete distributions. The binomial distribution is a discrete variable distribution, and discrete variables are things that are countable. Now we're going to talk about continuous variable distributions, and the most important of these is the normal distribution. First, let's look at some examples of some continuous random variables, just to refresh your memory. The life of a battery would be something that is a continuous variable because time is something that you measure. Heights and weights of people, you measure heights and weights. Time it takes to commute to school, again, time. Salaries of Major League Baseball players. House prices in a community, and SAT scores. We've all heard about that one. So when you were in algebra, you learned about functions, hopefully linear functions, quadratics, exponential functions, logarithmic functions. Well, there's a function called the normal probability distribution function. Don't worry, it's scary and you don't need to memorize it. It was discovered by a German mathematician in the 1700s named Carl Friedrich Gauss, who many people consider to be one of the most important mathematicians, if not the most important mathematician. Anyway, if you graph this function, you get a bell-shaped curve, and it has a lot of properties. If you were to add up all of the area between the curve and the x-axis, you would get an area of 1. And remember, if we have a probability distribution, all of the possible outcomes have to total up to 1. So the other thing about the normal curve is that it's symmetric about the mean. So the mean is right in the middle, and the area on this side of the curve is the same as the area on this side of the curve. And it also means that the mean is equal to the median and it's equal to the mode if you have a normal distribution. And then the two tails of my curve, they extend indefinitely. They get closer and closer to this x-axis, but they never touch. And if you're familiar with mathematical terms, that means that they have an asymptote. So that is the curve that makes up the standard normal distribution. So something is normally distributed. If something is normally distributed, the total area under the curve is equal to 1. If we look at the distribution, it's mounted and symmetric and extends indefinitely in both directions. It approaches but never touches the horizontal axis. The distribution has a mean right in the middle, and it's equal to no standard deviations, and a standard deviation of 1. The mean divides the area in half, 50-50 on each side, and nearly all of the area, almost all of that 1, is between a z-score of -3 and +3, also known as a standard score. The area under the curve represents the 3 P's: percentage, proportion, and probability. We'll use them interchangeably. And if something else you'll remember about the normal distribution is the empirical rule. We looked at this before. You'll see that the mean is right in the middle here, and that within 1 standard deviation below and 1 standard deviation above, that my standard score is -1 and +1 respectively, and that 68% of all my data is within 1 standard deviation. So the area here would be 0.68, which if I divide it in half is 34% on each side, or 0.34. Within 2 standard deviations, I have a z-score of -2 and +2, and 95% of all your data will lie within 2 standard deviations. Anything outside of that is considered unusual. And 99.7% of data is within 3 standard deviations. So the z-score or the standard score for that would be -3 and +3. All right. So the way you find the area under the curve would be you would need the standard score, and that will give you the probability or the percentile. So if we want to find the area under the normal curve that's less than a z-score of -0.65, we have to use well, in class we'll learn to use a calculator, but for now we're going to use a table for that. A table that somebody made for the days when we didn't have calculators. And again, a z-score is a standard score, and that just tells you where you are among a normal curve or on a normal curve. And the middle is no standard deviations, so a -0.65 is, if this were 1 standard deviation, is going to be somewhere on this side. And if I'm looking for everything less than that, I'm going to be looking for this area here. And that'll give me the percentile or the probability of something happening, or the percentile that a score falls within. So I need a way of figuring out what this corresponds to for percentile. So I'm going to go to a z-table. You'll have a positive z, a table with positive z values and a table with negative z values. This one is the one for negative z values. And you'll see here at the corner is the z, and you'll see numbers across the top and numbers down the side. We want -0.67. So if I look here, -3 is too low. And down here, 0 is too high. So I'm going to be looking for 0.6. So if I follow down here, let me get my highlighter out. If I follow the numbers, I have -0.1, -0.2, -0.3, -0.4, and here is -0.6. Right there. All right, so, but I want -0.67, and to do that I have to find the 0.07. So I'm going to go across the top. Here I have 0, 0, 0, 1, 0, 2, all the way down to here, 0.07. And you'll -0.6 plus -0.7 is going to equal -0.67. So that's the two numbers I'm looking for. Down the side here is where I'm going to find the tenths place, and maybe a decimal if I had a decimal, or I mean a integer. And across the top here is the hundredths place. And then I need to find out where these two values intersect. So it looks like this is my value, and that's going to be 0.2514. So the proportion of the area of the curve when the z-score is less than negative 0.65 is going to be 0.2514, or 25.14%. So if I draw that again, this is where the z-score would be 0, or the standard score. Somewhere around here would be negative 0.67. That means that this area is 25%, or roughly 25% of that area under the curve that totals up to 1. All right, second example. Let's find the area under the normal curve that's less than 1.52. If I draw a normal curve, that's an ugly normal curve, positive 1.52 is going to be to the right of that. It's actually going to be further to the right, but just for the purposes of this will be fine. And I'm looking for the, no, I'm not looking for that area. I'm actually looking for this area here, because I'm looking for less than. All right, again, I need to go to a table. This time, you'll see that I'm going to a table of positive z values. And I'm looking for the area to the left of 1.52. That's a 7. It needs to be a 2. So I'm going to go from and find 1.5, because you'll notice again I only have to the 10th place in this column here. And then across the top I'm going to have to go and find 0.02, because 1.5 plus 1.02 is going to give me 1.52. So if I follow this column, it starts at 0, ends at 3.5. I'm looking for 1.5. And then I'm going to go over to the 0.2 and figure out where these intersect. And they intersect at 9, looks like a 3, 5, 7. Do I need to get my glasses fixed? So the proportion of the curve that's to the left of 1.52 is going to be 0.9357. And it's going to be important as you do these problems that you sketch a curve and shade in the area that you're looking for. It'll help you, I promise, because they get more complicated than this. All right, let's find the area under the normal curve that's greater than 1.52. So this time, I really am looking for this area here. The problem is the table that we looked at finds the area from negative infinity to the point or the value that you look up. And our problem is that we need the area from the value to the right. Luckily, since all of the area adds up to 1, we'll call this area A, area B. If I were to add up those areas, they would equal 1. We're going to use that fact to help us find just the area here, what I called area B. And we're going to use algebra. If I subtract A from both sides, area A, then I'm left with area B. So we're going to actually fill in the values here. So I have 1 minus, and remember area A was 0.9357. So that just leaves me with the area 0.0643. So that's my final answer. Z greater than 1.52 has an area of 0.0643, or 6.5% of the area roughly. All right, now I want to find the area under the normal curve between negative 0.65 and 1.52. So first let's draw what that looks like. So I have some value of my curve here and a value here. And I want to find this value. Well, I know that the area here to the left of 1.52 was 0.9357. Now, if I want just the area in the middle, if I subtract this area here, the area to the left of negative 0.65, then I'm going to be left with just this area that I'm looking for here. And if I go back to the problem I did before, that was 0.2514. And that's how you get an area in the middle. And that leaves me with 0.6843. So 68.5% of data is within these two values. Why don't you try this one? Find the area under the normal curve between 1.68 and 2.75. Note that those are both positive z-scores, and that you'll need to look both of those values up in the table because we don't have those yet. So pause the video and restart it when you're ready. Okay, so let's draw a picture of this. We need 1.68 to 2.75. And if we looked up, so again, we want to find the area to the left of 2.75, and then we're going to subtract the area to the right, or to the left of 1.68. So we need both of those values. And I get for 2.75, 0.9970 from the table. And to the left of 1.68, I get 0.9535. And that leaves me with 0.0435. So the proportion of the curve that's between a standard score of 1.68 and 2.75 is 0.0435, or just a little over 4%. Okay, sometimes often you'll have to find the standard score before you actually calculate the percentage or the proportion. And you'll remember that to find the standard score, it's equal to your data point minus the mean divided by the standard deviation. So here we want to find the area if our x value is a continuous random variable that's normally distributed. It has a mean of 25 and a standard deviation of 4. And we want to find the value of the area between our data values of 25 and 32. If I draw this out, here I'm given the mean. The mean is 25, and one standard deviation is 4. 32 is above 25, so it's somewhere above 25. And let's calculate the z-score. Well, I already know that 25 has a z-score of 0, or a standard score of 0, because it is the mean. What I don't know is the standard score for 32. So let's calculate that. So 32 minus the mean divided by my standard deviation gives me a z-score of 1.75. So I'm looking for this area between 0 and 1.75. That means that I need to find the area to the left of 1.75, and then I'm going to subtract the area to the left of 0. Without looking it up in the table, what is the area to the left of 0? Hopefully you remember that it's 50%. That way it's one less value you have to look up in your table. So when I look up 1.75 in my table, I get 0.9599, and if I subtract 50% from that, I get a value of 0.4599. And that's my answer for that one. All right, give me a second to erase all this stuff. Need a bigger eraser. That's not an eraser. Okay, this time I want to find the area between the scores or values of 18 and 34. So I need to, well, first thing I'm going to do is I'm going to draw a normal curve over here out of the way. 18 is below the mean somewhere, and 34 is above the mean somewhere. So I'm looking for this area between the two. I need to find the z-scores. So 18 is the value I'm looking for, 25 is my mean, and 4 is my standard deviation. Gives me a z-score of negative 1.75. Same thing for 34. Plug it in for the value that you're looking at. Mean is 25, 4 is my standard deviation, and that gives me a z-score of 2.25. Now I'm going to look those values up in the table. Before I do that, I'm just going to remind you that you're going to look up the value for 2.25, and from that you're going to subtract this value here with a z-score of negative 1.75. All right, looking up in the table 2.25, I get 0.9878, and when I look up negative 1.75, I get 0.0401, which leaves me with 0.9477, almost 95%. And that makes sense with our values. Okay, Now we want to find the value of a curve to the right of a value of 55. We know that our mean is 40 and our standard deviation is 5. If I draw that situation here, this would be 40 and 55 would be over here somewhere. So we're going to need to find this z-score. And we actually really want this area, so we're going to subtract it from 1, just like we did before. So the standard score, or the z-score, is going to be 55 minus 40 divided by 5, which gives me a standard score of 3, or a z-score of 3. And looking that up in the table, that's 0.9987. We need to subtract that from 1 because we're looking for this area, not this area. So we have less than a tenth of a percent, or around a tenth of a percent is greater than 3. All right, if we look at the probability of our value being less than a value of 49, this one will be easy. I draw that in. 40 is my mean. 49 is above that mean, and I'm looking for the area less than that. So I'm looking for the area to the left, which means I just have to look up the z-score or the standard score, and I don't have to add or subtract or do anything else. So I need to find that standard score. 49 minus my mean 40 divided by 5, my standard deviation, gives me a standard score of 1.8. Looking that up in the table, it's going to be 0.9641. Here's one for you to try. Turn this off and restart it when you're ready to check your answer. All right, let's find our z-score. 30 minus 50 divided by 8 gives me a z-score of negative 2.5. And then the standard score for a data value of 39 gives me a standard score of negative 1.375 or negative 1.38. Drawing a picture of what I need here. I need that area between these two. That means I'm going to look up the standard score for negative 1.38 and subtract the standard score for negative 2.5. When I do that, I end up with 0.0784. A few more for you to try. Pause this, and when you're ready to start and check your answer, start it back up. Okay, so I'm looking for the values between 70 and 135, or the area that's between those two values. Again, I need to find the standard score, and the value for 70 is going to be negative because it is less than the mean of 80, and I get negative 0.83. And the value for 135 is going to be positive because it is greater than 80. Actually, it's really positive. That you will not find this in the table. The table only goes up to values of 3. But let's draw a picture of the situation. We need negative 0.85. Oh, that's pretty negative. It's not quite that negative. And then values out here, 4.58. So because we don't have values of 4.58, remember that 99.7 of the values are between -3 and +3. We're going to use the value of 1 because essentially, if you were to round, that's what you would have. And then we look up the value for negative 0.85. When I subtract those two values, this value from 1, I get 0.7967. And then the last one is really straightforward. We want area to the left of 27. So we want this area. We know that it's a negative z-score because 27 is significantly less than 80. That gives me a z-score of negative 4.42. Again, we don't have that value in the table. And if I were to round, if I did have that value and I were to round it to 4 decimal places, I would have 0. So that's it.